Hi, good morning, everyone. Thank you for coming to this seminar. So I think we're gonna gradually starting this talk series of talk. First of all, I'm very happy to, very also honored to introduce Inami Laboratory from Tokyo University. So today's talk is kind of special. We have a speaker and so you will hear about the three series of the talk in this kind of 45 minutes something, and then you also have some 15 minutes kind of question and answer. So okay, so let me introduce the seminar about the JIZAI Body, the Beyond Human Limit by Limit. So the Inami Laboratory is coming from the Tokyo University Research Center of Advanced Science and Technology. And then their focus is that as you can see, JIZAI Body, this is like using technology, computational, also computer technology and robotic technology to go beyond our human body limitation. And then those kinds of questions giving us more like to me think about like how society should be and also how we understand ourselves, something like that. So today, because Inami Laboratory right now is kind of visiting my lab, and then that's a very nice opportunity to also show their work in the oyster community as well. So today, I want to introduce three speakers, project lecturer, Azumi Maekawa, and assistant professor Yasuaki Monnai, and Professor Masahiko Inami. The talk should be in that order. Okay. So let us start the talk, and then it's starting with Azumi Maekawa-san.
Good morning. Thank you for introduction. I'm Azumi Maekawa, and so today I start my presentation titled with Motion Design Bridging Humans and Machines. So this is my brief introduction. This is my education and work experience. I completed my PhD course at 2021, and after working as an assistant professor, I currently working as a project lecturer at the Information Somatics Lab, that Inami Lab. So today, I introduce my several works. my research motivation lies in how we can update the classic relationship between the humans and machines. So, and I investigated from the perspective of motions, so the machine's motions. So in this context, I will introduce some of my work. So first of all, I start with work related to the relationship with machines as others. So my interest lies not in machines that helps people through practical work, but in how to design motions that are attractive to humans. So specifically, from perspective of the lifelike motion, I worked on designing machines as others, such as other people or other living things in our environments. So first, we focused on working motion. So instead of the heavy motion often associated with these robots, you can see the left side. So we explored how to design a walking motion that is more lightly motion, similar to that of living things like a bird or something. So here's the working robot I developed. So in this time, by using quadcopter, so we propose an approach that frees the legs from their role of supporting their bodies and use them more for appearance, more focusing on appearance and impression of movements. This is a system designed to generate leg motions for quadcopter that appears like that locomotion like motion. So the leg movements are generated in real time using the motion generator acquired with reinforcement learning. So we designed the learning process. We designed the learning levers with the goal of reducing the speed of the foot touching of the ground, And so this is mean that to prevent the robot's foot from sliding on the ground. So finally, the motion is created by feeding the quadruped motion to that motion generator, and finally we get that. So get walking like motions. So and so interesting point was without the limitations like the joint space or joint range, joint limitations, so that the type of motions cannot be emerged. So this is means. So I think that this suggests the importance of the physical body's constraints is important for acquiring some skills or abilities or motion. So sophisticated skills. So and this is the next project, and the second one. So is a robot made of 3 branches, as you can see. So this project also focused on the walking motions emerged from the shape of the bodies. The inspiration for this project is in the concept of the found object. So a found object refers to natural materials, ready-made, or things present in the environment. So where many artists find values or some function to these materials. So in this project, by structuring these objects, so it's structured found these objects and structured these objects as a kind of, so to find as a kind of function or values. The idea is explored to how to apply these concepts to the robots or robotics or some automation technologies. For this approach, we also used the reinforcement learning, so to allow the machines to provide meaning or some values or function. So we collected 3 branches and then 3D scanning it, and so connected them to develop, to make some robots, and then conducted a learning process through the simulated environment. The goal was to move as far as possible, which we can consider as working in this time for these machines. In this process, for example, the type of robots managed to convert irregular shapes like Y-shaped branches into some functional use, like propelling their bodies. So in this project, so we're focusing on using the irregular shapes into some systematically systematically. So try to use systematically. So this is a similar type of project, and why? So the previous work is focused on the walking motion, but this focused on the standing up motion. So in this work, I try to show learning process itself, and I created the work where the machines learn in real time in physical world, and show the process for the people attending the exhibitions. So in this project, so the robot's goal is to increase the height of it, and learning to increase their height of the center of gravity. And this is a very, I think, very attractive motions emerged in some using the unique shapes and images unique motions. So often I have published the academic papers as these on these works. But so the key is the visual appearance and the impression they make. So I have focused on the presentation and exhibition styles. And in this way, these activities involve in the exploring some robots or artifacts or some kind of machines that move people emotionally and inspire, how to inspire them. And then move on next topic, machines as augmented self that I am investigating through human augmentation research. So originally humans are augmented using or through technologies. So especially my research interest is in the augmentation of everyday dynamic movements carried out in our personal spaces. So, and how this could alter or update our human perception and behaviors. So this is an example of the work. In this project, I tried to enhance balanceability using the tail-like device. This tail has a weighted tip and moves behind the users. And it provides a reaction force and torque to the users without touching the surrounding environments. The device is controlled according to the center of pressure measured with the sensors under the foot. And as a result, we found that the device improved the user's balancing ability 20% on average. So, however, even if the technology is used to enhance performance or results, so if the users cannot recognize it as their own result or doing, so it will not lead to a sense of achievement or a sense of self-efficacy. So this research question is how to attribute extended abilities or obtained the improved performance or results to the users themselves. So this is a project with these motivations. So these two persons play tug of war, but it seems to be a little bit different because the win or lose is controlled by a third person. So this system is very simple. There's a machine pulling the rope from behind the users and provide the assistive force. And the rope has several force sensors and detect the player's performance and action in real time. So the important point is how to present assistive force. So if force is simply applied, the user will feel that they are assisted. So and they lose their sense of agency and cannot concentrate on the playing games. So in this project, we focused on how to control the assistive ratio in real time according to the user's actions. So by controlling the force applied to the rope appropriately, so users cannot notice that the assistive force during playing the game. So leveraging this type of control assisting force, the system that may enable to fully engaging in sports activities for various people, such as adults versus children or something. So, and we may update some type of sports. And this is the next work. So this time the work focused on how to intervene in terms of timing and leading to integrating humans and machines. In this system, the users can use the handheld device, and the device control the only release timing and sensing motion from the motion capture, and the device release the object in desired timing by calculating the trajectory in every time. So this work also suggests in several exhibitions and interestingly, so we installed the dummy button to the device, and so using that, so that we find that we can control the performance without the users noticing the intervene of the system. So I mean the users, we can control the users' performance without noticing the users. That's the external control. It suggests that utilizing the timing, so we can enhance our performance with the machines without losing the sense of agency. So next topic is also how to implicitly intervene in the position. So we focusing on the remote sports. So it is difficult that we can communicate in the remote in real time, but in sports it needs the high so the sports needs fast responsive action or some fast movements. So it's difficult to develop in remote style. So we developed the test bed for these remote sports. So it consists of the remote machines and the interface to control it. The bottleneck is the communication delay. So it's prevent the user from playing well. It means that users cannot respond to the opponent player's actions in real time. So we propose a method where the machine starts moving before the user begins to move. So by utilizing such kind of delay. On the other hand, so we found that limiting the machine's autonomous time to just a very short time, so the performance could be improved while maintaining a sense of agency. So using these systems, we can provide a remote sports experience in regardless the users is where the locations. So finally, I discussed the topic of how can we design machines as a new tool. So the project tried to enhance conventional tools by attaching the wearable device. The unique point is wearable, but it's handheld device. So it provides a force to the tools, and we can change the several tools in the specific situations. We can enhance these skills using these tools. So this is the system overview, and the force is provided to the tool, and so we can maintain the naturally contact condition to the tools with our hand, and the reactive force is provided to their forearm, but the sensitivity is difference between the fingertip and the forearm, so we can feel as if the external force provided to the tool. So as a result, so this is the possible application example. So for example, we apply to this device to the sculpting. So we controlling this device when the users invade to the desired shape. So in that time, so the device provide the reactive force and assisting the motor skills. So finally get some kind of the sculpture. So this is the result obtained by the novice users, not experienced to not has the sculpting experience. So, and some kind of virtual reality haptics. So it's a unique point is the wearable, so it can render some large space objects. And this is the remote collaboration example. So the left person controlling and other some function or something to the remote users' motions. Okay, so next one is the final one. So that this is the supporting design of wearable robotic arms system. So this is there are a lot of wearable robotic arm projects, but these robots is designed on focusing on the spot that project in that project. So we support these some type of these wearable robotics. So this system consists of several steps. So input the user's pose and define the motion range and space or the degrees of freedom, and fabricating it with standardized some parts and assemble it and providing the controlling motion examples. So this aims to improve prototyping process and accelerate this kind of wearable robotic research. So today I have introduced several types of machines and from the perspective of motion design. So while each topic presents its challenging, such as different properties, methodologies. So, but I try to advance my research by revising these differences. So that's all. Thank you so much.
So next speaker is Yasuaki Monnai. He will also talk about slightly different topics, but it should be also very interesting in this field.
Okay, thanks for introduction. I'm Yasuaki Monnai. I'm an associate professor in this group. And I joined in this group in 2021, so it's close to 3 years already. And today, I'm happy to have a chance to share our recent research projects with you in OIST. And my talk is about wireless for wet wear. I'm basically interested in a wireless technology and now developing a novel technology that connects between the dry and wet. Okay, our biological body is, of course, composed of numbers of a massive bundle of nerves. Those are wires. And our body is, of course, wet to be a platform of chemical reaction. On the other hand, our conversation, for example, is a wireless process, which is dry. We exchange acoustic wave and optical wave propagation. And of course, when we are connected to the internet, we use laptops or we use smartphones, and those devices are communicating with each other via microwaves, which is also a wireless and dry process. So in this way, the wired wet systems and the wireless dry systems have very different natures. And the connection between the dry wireless and wet wired is always a matter. And for example, when our brain tries to get the information from the external, we read text, we watch displays. That's one example of connecting the wireless and dry and wet. And also another layer of the example will be, for example, we have invasive and non-invasive electrodes on our body, and that reads and writes electrical signals in your body. Another similar example would be we put a mechanical contact probe on your skin to send and receive ultrasonic signals, to read and write acoustic signals in your body. But I would say those connections between dry and wet is sort of slow speed and not smooth and rather tedious. And is there a way to better connect between those dry and wet environments? That's the basic motivation. And so here's our research project portfolio. not all, but many are related with telehealth technologies. So what is telehealth? Telehealth is an electromagnetic spectrum located between the conventional radio wave and light wave. And during the 20th century, it was difficult to artificially control this frequency spectrum. But today, it's becoming possible to use this frequency range. And among many of the potentials, here today, I'd like to emphasize and point out that telehealth has an affinity with ultrasound. Ultrasound is, of course, an acoustic wave. High frequency acoustics is an ultrasound. And telehealth wave is an electromagnetic wave. So they are different physics. But there is one thing in common, that is the wavelengths. Telehealth waves at 300 gigahertz has a wavelength of 1 millimeter, whereas the ultrasound at 300 kilohertz has also the wavelength of 1 millimeter. They are in the same range. This is because light speed and the sound speed is different by the factor of 10 to the power 6. So the terahertz ultrasound, terahertz electromagnetic wave and the megahertz ultrasound has the same similar wavelengths. That's one similarity. And there is also one striking difference between the terahertz waves and the acoustic waves. That is about the absorption in the medium. Terahertz can propagate in air in a free space, but it's highly absorbed in water. The terahertz doesn't propagate in water. And in ultrasound, for ultrasound, it's complete opposite. Ultrasound can propagate in water, but it doesn't propagate in the air. So there is one striking similarity and one striking difference, complementary feature. We could expect some interesting interaction between those two modalities. Okay, indeed, ultrasound has been already applied in many fields to access the inside of the body, which is not possible with microwaves. And you might be familiar with ultrasound echo imaging, but ultrasound can also be used for data transmission through the biological samples. But there is one fundamental limitation for ultrasound. That is, we always need mechanical contact between the skin and the transducer pores. This is in order to establish the acoustic impedance matching. So we cannot use ultrasound without mechanical contact on your skin. However, it is indeed possible to generate ultrasound in the medium in a non-contact manner, which is known as an photoacoustic effect. It is a well-known effect, firstly reported by Graham Bell, and it turns light into sound. And here I simply explain the process. For example, we irradiate the sample with electromagnetic wave or optical radiation, any kind of optical radiation. And then the sample, of course, is heated up. And what if we modulate the irradiation on and off, switch the irradiation on and off, then the sample temperature increases and decreases and increases and decreases. In this way, sample temperature changes cyclically, periodically. And some temperature change involves the change of the volume because of the thermal expansion. So, and the change of the volume also involves the change of the pressure. So if you alternate, if you on and off the irradiation 1 million times per second, then you obtain the ultrasound of 1 megahertz in the sample. So that's a basic principle of the photoacoustic effect. And the important factor is alpha here, which is an absorption coefficient. And as I mentioned, the terahertz radiation is highly absorbed in water. So terahertz radiation could be suited to be combined with this kind of photoacoustic effect. And indeed, it has been demonstrated that by using a very strong short-time pulse, terahertz pulses, and irradiating it on the water sample, the acoustic ultrasound pulse was generated in a water sample. However, in this demonstration, the terahertz pulse, the very strong terahertz pulse, was generated using a so-called free electron laser, which requires a very huge facility requiring a dedicated building. So is it possible to make it handy and more applicable to our human body related applications? And indeed, we did it. And we shifted from the time domain short time pulses approaches to the frequency domain approaches. And we constructed a system composed of terahertz oscillators and high-speed modulators, high-power amplifiers, and also a local amplifier. By combining them and operating them in the frequency domain, we could generate and detect ultrasound in the water medium with a sufficiently high signal-to-noise ratio. Okay, so this is the schematic of the experimental setup. And what we did was to prepare a water tank with a side length of like 30 centimeter and fill the tank with the water. And indeed, we think this is a kind of model of the human body. Human body also has the same dimension, and it's a kind of water bulk. And inside the water tank, we put a toy of submarine, and submarine is controlled by the ultrasound. And this ultrasound is generated by the sub-terahertz irradiation. So the important point is that this water tank is isolated. We do not have to attach any mechanical contact probe or transducers to this water tank because the ultrasound is wirelessly generated. And remember, this is a model of the human body. So this submarine toy could be replaced with any devices like micro robots or capsule endoscopes or any other devices in your body. Okay, we did analyze the generation process of the ultrasound using terahertz radiation, and we reviewed the important impedance effect of the wall of the tank. So we got a kind of prescription to further optimize this process. Okay, and that was about data transmission using ultrasound, but ultrasound is of course more widely used for imaging applications. And today, recently, many groups worldwide is developing a wearable ultrasound imagers transducer. And by means of printed electronics, many groups are trying to develop wearable transducers. But still, we have to wear with these approaches. And we also have to put some gels or need some sticky materials to establish the mechanical contact for acoustic impedance matching. And is there a way to fully remove those devices from your body? And we I would say we have succeeded in this approach, in this challenge. By irradiating the sub-terahertz radiation on your hand, and then we demonstrated that spatial distribution of the bones and meats resolved in this way. And I said half succeeded because the transmission process, the ultrasound generation is fully non-contact. That's a good thing. But still, we have to, at the moment, we have to rely on the contact detection process for this approach. So backside of this hand, there is a hydrophone, which is in contact with your palm. So now we are trying to also remove this hydrophone and try to detect the acoustic signal wirelessly in a non-contact manner. Okay, and this kind of the similar photoacoustic imaging has been developed in the infrared regime, infrared ranges. And the famous example is blood vessel imaging using infrared photoacoustic effect. So in this case, it is based on the fact that infrared light is absorbed by blood. So the blood or blood vessels in your body become the source of the sound in the case of infrared. But in the case of terahertz, we don't need blood. Or blood is not the source of the sound, but water becomes the sound of the source of the sound, right? So they have different features. They have different, I would say, strengths or the different applications. And using terahertz, we think it could be replaced. It could replace the contact type transducers, so that selectively excite generate the signals from the blood vessels. They have different applications. And one possibility that we demonstrated is the non-contact estimation of the sample stiffness. And here, inside that red container is 3D printed, and inside the container, there are chain gel with a different compound. And we try to estimate how hard that gel sample is without touching the sample. And we did it by irradiating the subteraceous radiation and listening to the emitted ultrasound using the microphone. And we could clearly distinguish the sound frequency differences. So that's one possibility enabled by the fact that water becomes the sound. Water becomes the source of the sound. Okay, my talk was about the connection between the dry and wet situations. But now in this slide, I would like to focus on the outside of the body. And I'd like to introduce the terahertz radar. And maybe you are familiar with millimeter wave radar equipped in the recent cars. And by scaling, by changing the carrier frequency of the radar, we could straightforwardly implement terahertz radar. And by increasing the carrier frequency, we can expect the scaling effect, which means the higher spatial resolution and also the device footprint becomes miniaturized, smaller, because everything becomes scaled down. And this kind of capability to detect the minute motion, minute displacement, could be used to sense the information from the human body as well. But unfortunately, there are many technical limitations in the terahertz regime at the moment. So we cannot directly translate microwave approaches or optical wave approaches. So we need to come up with a novel solution or radar architecture that is applicable in the radar terahertz regime. So I'm not going into the details today, but we developed some tricky hardware to do some analog signal processing in the hardware layer, which is applicable in the terahertz range. Okay, and by using this kind of radar, by implementing such a radar, we demonstrated to use it as a non-contact stethoscope, which can detect the minute motion of the skin. And this red curve shows red data shows the result read out from the terahertz radar, whereas this blue curve is the ECG electrocardiogram. They show a high correlation, and we could detect the very small motion of the skin surface without touching. Okay, in this video, the type of the architecture of the radar is a bit different, but the result looks the same. Okay, lastly, I would like to shortly mention about the wireless communication. It is important to note that the gap between the wired communication and the wireless communication is becoming smaller and smaller. And today, the 5G network is already commercially available. But we think the neural data in future will be too big and not really easily handled by the 5G communication capacity. And my point is that 8K movie, for example, is a representative data demanding application in the 5G scenarios. But by considering the product of the amount of the information in the temporal axis and temporal direction and the spatial direction, we think the amount of the data that should be handled in the BMI will be even larger than the 8K movies. And this will be totally above the capability of the current 5G technology. So maybe 6G or 7G will be able to handle it. But in that case, the broad bandwidth of the terahertz radiation will be very, very beneficial. However, when we want to use terahertz radiation for wireless communication instead of the conventional microwaves, there is one fundamental limitation problem. That is, it's not easy to link between the points because the wavelengths become shorter than the microwaves. So we need to transmit the signals with highly directional beams, and highly directional beams is easily intercepted by human bodies or furniture or many things. So we definitely need beam steering for the terahertz radiation. However, it's discussed that terahertz beam steering is still not efficient and practical at the moment. So to circumvent this challenge, we demonstrated some novel approach for terahertz beam steering and recently extended it into 2-dimension. And I shortly mentioned it. And this is enabled by implementing a virtual lens. Virtual here means we do not need dielectric materials to implement lens, but we just prepare some metal structure and we design the boundary condition of the system so that it behaves as if there is a dielectric material. So this is the concept is very similar to the virtual reality. And by doing so, we could implement a very minute motion, mechanical displacement in the system. And this minute displacement, which is not visible with the eye, can deflect the beam in a very large angle. For example, when you are using an electric fan to blow the wind, suppose you want to rotate the wind direction over 60 degrees, you need to rotate the electric fan for 60 degrees. That's a common sense. But in this case, we only need to displace the device very small in a very small displacement. But the output beam, emanating beam, can be deflected in a large way. So there is a leveraging effect. And yeah, in the beginning, we demonstrated only one-dimensional horizontal beam steering, but recently we extended it into 2D. And today we don't go into details, but hopefully I can introduce it more in detail in near future. Okay, so that's the end of my talk. Sorry, a bit in a hurry, but we're developing a novel wireless technology connecting dry and wet world. Thanks for your attention.
Hello, I'm Masahiko Inami. So I understand. So you are still curious. What issue? What is issues in our laboratory? During this session, so I just got a good news. So that is about our alumnus. One of our alumni students, so when I worked for Keio University, so just chosen as finalist of Nebula Award. So this year. So I'm really proud of her. But so let me back to our story. So actually, so we have 7 staffs in our laboratory. So we are focusing on information somatics, how we understand our some information system. So it can control our body. That is our cognitive process, or understanding process, and also behavior process. So through information technology, this is our target. And this is our recent output. That is about we named this project as JIZAI arm. So let me introduce behind of this project briefly. So our one of our motivation is, so please imagine if in the metaverse, so you are transforming into a bird, how do you fly? Maybe you can use your arms like this. But so if you are transformed into an angel, how do you fly? This is still a challenging problem. Maybe so you need to use your arms, but how do you control your wings? So in order to challenge to this type of problems, so we have established new research projects. That is JIZAI Body project. That is virtual cyber project. So, and JIZAI is a concept in Hinduism and Buddhism. So being able to do as one precedes or doing at well, that is the original meaning of JIZAI. And so actually, so we have chosen as one of JST project, which name is JST Erato Inami JIZAI Body project. That is somehow digital transformation of our body project. And so we have 5 targets. That is augmented perception, augmented body augmentation, and outer body transformation, shadow cloning, and assembling. Actually, so Azumi's project is a part of this concept. And so this project will consist of 6 groups plus 100 plus members. Actually, so Shun Kasahara was a part of our group. So about 5 years ago, I think. five, 6 years ago. And so we have already achieved this various type of JIZAI body technology, such as balanced tail or extra limbs, and also some color sense and offshot output. And also, this is also significant research output. So it was mainly led by Professor Yoichi Miyawaki and Dr. Ganesh from CNRS.
Do you notice that there are 6 fingers? We, at the University of Electrocommunications, CNRS France, in the University of Tokyo, are investigating the future of human body augmentation technology in the JST Erato Inami JIZAI Body project. In this project, we are studying whether humans can accept new wearable artificial fingers. Attached on the hand is an artificial finger that we developed in the 6-finger project. The artificial finger is actuated by electrical signals recorded from the muscles of the forearm. The electrical signals from the muscles are measured by sensors attached on the forearm, processed by a computer, then input to a motor to control the artificial finger. How does our brain change when we use the artificial 6th finger for an extended period of time? The human brain has regions that are activated when we move our fingers. These regions are called the motor cortex and the somatosensory cortex. Previous studies have shown that specific areas within these regions are activated for each finger. Extended use of the artificial 6th finger may change the activation patterns in the motor cortex and the somatosensory cortex from those observed for innate finger movement.
Actually, so Professor Miyawaki found that the motor cortex for our pinky finger is a little bit shifted. So after this type of trials, so maybe so we are able to, it means we are able to adapt so new body schema. So as you show, such as 6 fingers. And so we have also developed not only body enhancement technology, but also skill enhancement technology or skill learning enhancement technology. So this is one example of skill enhancement technology by using virtual reality, but unlike so just a simulator. So we have developed so special virtual environment, so which time flow is slower. This is a sort of slow motion virtual reality. So thanks to slow motion reality, so even if novice user could acquire so somehow difficult skill. So because so in real time it's very hard to be succeeded. But so in slow motion reality, so even if me could easier to acquire how we handle such a juggling style. And so surprisingly, just after 3 minutes to 5 minutes. So this is me. So I could manage this type of juggling. So this is more complicated task. So this is slow motion and getting faster and faster and faster. And after 3 minutes, 3 to 5 minutes. I'm really happy. And so last year, so I just acquired this skill. So I was really happy. So if you are interested to acquire this type of kind of juggling skills, so please let us know. So you are able to acquire this type of skill within 5 minutes. This is a unique point. Maybe, so I believe, so the reason why we are able to get this type of skill much faster than so real environment is, so one key is maybe running based on learning curve. Maybe so we are able to acquire new type of skill. So based on when the ratio of success and failure is correct ratio. or correct numbers. And so I just failure more than 10 times or 100 times, I just ignore or I just abandon. But so if we are able to prepare a correct condition to acquire, so success and failure ratio, so we can easy to acquire this type of skills. And then, actually, so let me move on to the next topic. That is about science engagement. So actually, so when we developed extra limbs or 6 fingers, so some people really ask us, so become really scared to our research. So output or social implication of our technology is utopia, dystopia, and in order to connect or manage this type of social engagement. So of course, so as a researcher, we have published a book, and so we have established startup companies. And so we also conducted some scientific event or technical event for the public, the science museum. And so we have also developed Lego-based 6 finger. But this is quite nice. And so students and kids are really happy to develop their own 6 fingers. And so also we have spread paper craft of 6 fingers. But like that. But still, so I found a large barrier between science and technology lovers and those who are not. And so in order to lift this barrier, so we started to use new type of engagement style, so which feature gadget, art, and sports. So in the first strategy, so we have developed new gadget, which name is JIZAI Face.
JIZAI Face。
JIZAI Face は自由自在に遊べる人工身体部位です。カメラの目、スピーカーの口、マイクの耳、匂いセンサーの鼻といった顔パーツをそこら中にくっつけて、自分の体の延長、代替としてこの世界に存在させることができます。例えば、離れた相手と。
今日回転寿司行ってきたんだけどさ。
それで
一人で30皿も食べちゃったの。やばくない？
マジでそれはやばいわ。昨日寝てないのよね。
そうなの？大丈夫？も
う。例えば、外にいる相手に。
どっちだったっけ？
そこは右やで。いや、そこは右やって。
そうだったね。
そう。もうすぐやで。
あ、そうかい？
さらに、AI エージェントにも対応。Hey、自在。今何時？
午後2時50分です。それでは、良い一日を。
So actually, these gadgets are really appreciated among younger generations. So when we have demonstration at our open campus, so a lot of kids are stuck into this gadget, and so we also try to collaborate with industry designer. So his name is Professor Yamanaka, and also establish new type of art performance, which uses extra limbs or supernumerary limbs. And this is JIZAI project.
Digital cyborgs, powered by wearable robotics, raise important societal questions about their integration into our world. We explore intriguing questions about our relationship with digital cyborgs. Will you share or exchange your body parts with others? Will we love our robotic body parts? Will you mourn and memorialize them after our death? To address these questions, we have produced JIZAI Arms, a wearable robotic system.
So this is JIZAI Arms, so designed by Professor Shunji Yamanaka. So now he's a distinguished professor at the University of Tokyo. And so they are JIZAI team members. And so fortunately, so our design project was chosen as have an opportunity to show our performance at the opening ceremony of the Ars Electronica last year, like that. It was really appreciated. And finally, so we also started to use sports for science engagement. So more than 10 years ago, so I proposed new sports project, which named Superhuman Sports, by using technology to enhance our abilities, and also by using technology to establish inclusive sports. And so these are some of our achievements of Superhuman Sports for these 10 years. So we have already developed around 30 superhuman sports so far. Unfortunately, so have you ever been to Tokyo Tower recently? Actually, so just after COVID-19, so Tokyo Tower, so inside Tokyo Tower, so they opened new esports park. So one of the hugest esports park in Japan. And so 9 of our superhuman sports was chosen as permanent exhibition at this esports park. You have an opportunity to come to Tokyo Tower area, so please do not miss to come to our or try our superhuman sports. And finally, so let me show you this video. So actually, she's a person who tried kendama, so at the first time by using our technology. She's training. So this is training. So this is so when I see this movie, so I was so surprised and also become happy because maybe our technology has power to encourage not only younger people but also elder people to acquire a new type of skill. And so even by using technology, many people become happy if they can acquire a new type of skills. So assistive technology or educating technology to acquire a new type of skill is still important to empower general public, I believe. Okay, thank you very much.